I'm having a little more difficulty than I anticipated doing the proof based on a sample point. Don't have any trouble understanding what I need to do. I'm having a little bit of trouble putting this into elegant notation. So the idea is clear enough. So I'm going to develop another idea here, but I'm not going to get to a proof, at least not a completely rigorous proof. Okay, so we got the same situation as before, some function f of x, y, an m times I and an n times j. We've got a point x naught, y naught. Instead of numbers, we're going to use symbols. And I'm going to have a sample point, x star, y star, somewhere within this interval. And using the sample point turns out to make the proof more cumbersome than it really needs to be, but I want to try to boil that down to something that might be a little more intuitive and useful. I'll also say that proofs of Green's theorem don't generally do it like this. There's a very facile proof, or at least the first step is very facile, that doesn't give any deep insight into anything. It's just a symbolic manipulation. I want to develop this in a way that's a little more insightful than the proofs that I usually see in textbooks. Okay, and related to the proof that I learned, 50-some years ago, the very first proof I learned of Green's theorem in the plane. Okay, anyhow, with that background, I want to look at, first of all, just the expression m of x star y naught plus delta y minus m of x star y naught over delta y. Now all that is the rate at which m changes, the average rate at which m changes from this point to this point with respect to y. So this is the approximation of my. Now I'll say that the limit as delta y goes to 0 of this expression is my at x star y naught. That's just an adaptation, just a little different notation than just replace some symbols in the definition of the partial derivative, and that's it. Okay, so we have this, so we can say that if this is a small rectangle and the function is not pathological, it's well behaved with continuous derivatives and stuff, so that my at xy is approximately equal to my at x star y naught. I could say for all x, y, et cetera, et cetera. I'm just going to say within the rectangle. Okay, so now if I want the integral of m dx, that's going to be the integral over path 1 plus the integral over path 2. Okay, well the integral of m dx over path 1 is the integral from x naught to x naught plus delta x of m of x y naught dx. And then it's going to be plus the integral from x naught plus delta x back to x m of x y naught plus delta y dx. Now, of course, this integral is in the opposite sense of this one. If we express both integrals as an integral from x naught to x naught plus delta x, well, we're just reversing the order of integration here. You know, the x increments that you use here would be negative. And just, okay, without going into detail, reversing the order of integration, for obvious reasons it should be obvious, gives us the integral of negative m of x y naught plus delta y plus m of x y naught dx. Now, what I want to do is I want to observe that this is just the numerator we have here, except I have an x instead of an x star. I'm going to divide this by delta y and multiply this by delta y being a constant. You can multiply it anywhere, but I'm going to put it on the end over here. Okay? I'm going to say that this then is, in a sense, can be made rigorous of debating what whether I want to write this, we'll just skip to the next, I'm going to write it. It's this, and I didn't put my arguments, the my in here, and I had plenty of room to do that. Might not have been a bad idea, but I'll smudge up the board a little. Okay, my of x naught of x y naught. And this is approximately equal to my of x star y star delta x delta y. Which itself is approximately equal to the integral of my of xy dy dx from x naught to x naught plus delta x and y naught to y naught plus delta y. Now these approximate equals need to be made more rigorous, and I'm still not sure it's really an advantage to go in terms of the sample point here because it makes the argument a little more expensive. I'm sure it's not necessary, but I kind of like the idea of using a sample point. Okay, so I've got to think about this a little bit more. But what do we have here now? We have then, well, this is a double integral of my over the region. This is the integral of m dx. Around the boundary, and of course dx is 0 on this boundary or this boundary, so this is the whole integral of m dx around the whole rectangle. So the integral of m dx is equal to the double integral over the region over the rectangle of my with respect to area. And it all comes down to just the fact that it's the y derivative of m that makes the magnitude of the integral over this top edge different than the magnitude of the integral over the bottom edge. A similar argument on n will give us that the integral of n dy, and I've lost something here. This step to this one, this is the negative of this expression. Needed a negative sign here, negative sign here, negative sign here. Because this one, it's the m of x, y is subtracted from the m of x, y naught plus delta y, and here that's backwards. Okay, so it should be negative. But okay, the integral of n dy is then equal to the integral of nx with respect to area. And I said, so this and as delta x goes 0 and delta y goes to 0, we get this. Of course, in the limit, as delta x and delta y both go to 0, these integrals are both 0, so that's not really right. I could say that the integral of m dx over negative double integral of my dA equals 1. And I can torture that along with the analogous argument here with some more formal operations and limits into a proof, and maybe prove to myself that doing this in terms of sample point is unnecessary. I still like the idea.